Hello everyone, welcome to the newest video in our library. We're going to be talking about confidence intervals and what they are, what they mean, how do we find them, all the good stuff about confidence intervals you ever wanted to know but were afraid to ask. Alright, so as a preview, in the last chapter we looked at sampling. Starting with a large population, we imagined taking many samples and we deduced how some sample estimators such as p-hat and x-bar were distributed. In this chapter we do the reverse. Instead of taking many samples, we're going to say if we're given one sample, what was the random system that generated its statistics? This shift from going from many samples to one sample represents a change in our mode of thinking. We're going from deductive reasoning to induction. And this begins our study of what we call inferential statistics, which is the type that we're going to be doing from here for the rest of the year. So here's an example. Let's rate your confidence. I want you to pick a number between 0 and 100 based on the questions that I'm about to ask you. So get the number in your mind. First, do you believe you could guess my age within 10 years? Okay, you probably picked a pretty high number. You're probably pretty confident you can get within 10 years. What about within 5 years? Your number is probably maybe still high, but maybe not quite as high. What about within 1 year? Alright, so what should have happened there, what I would expect it to happen, is within 10 years you're probably very confident. Within 1 year, maybe not so confident. Okay, what about an athletic scenario? Let's say I want you to shoot a basketball at a wading pool. Do you think you can make it? Rate your confidence. Alright, probably pretty high. Wading pools are pretty big. What about shooting the ball at a large trash can? Okay, probably still pretty high. What about if you're shooting the ball at a carnival? Do you feel as confident shooting the ball at a carnival as you do shooting at a wading pool? Probably not. So the bigger the area, the bigger the interval that you're interested in, the more confident you are. The smaller the area, the less confident you are. So that's basically what happens. Well, that leads us then to something called a point estimate. A point estimate is where you use a single statistic based on sample data to estimate a population parameter. It is the simplest approach, but it's not always very precise due to, as we've seen many times in class, the variation in the sampling distribution. Every sample is slightly different. Why can we use a single statistic based on a single sample to make an estimate when we know that samples vary? So here's an example of a point estimate. Brian and Ben park next to each other in the HH parking lot. Ben believes Brian's a bad parker, parks too close to him every morning. So last week, Ben decided to apply his knowledge of statistics to prove his point. He used a measuring tape and he measured the distance between their cars each morning. Monday, 12 inches, Tuesday, 14 inches, and so on. Ben calculated the average distance between their cars to be 15 inches. This is a point estimate. It doesn't take into account the variability between weeks. Some weeks it's rainy, some weeks it's snowy, some weeks it's sunny, some weeks Brian had breakfast, some weeks he didn't. Things change. So point estimate is very easy, not always very precise. That then leads us into confidence interval. A confidence interval for a population characteristic is an interval of plausible values for the characteristic. It is constructed so that with a chosen degree of confidence, the value of the characteristic will be captured inside the interval. We use confidence intervals to estimate unknown population means. Since a point estimate is not precise, statisticians like to give intervals. We don't like saying we believe that the population mean is exactly this. Instead, we like saying we believe that the population mean is somewhere between these two intervals. The formula that we use is we take our estimate, our point estimate, and we plus or minus a margin of error. You should hopefully remember this from 9th grade. Now, point estimates we know. Those are means, p-hats, things that we determine. Margin of error, here's the new stuff. The margin of error shows how accurate we believe our estimate is. The smaller the margin of error, the more precise our estimate of the true parameter. Here's the formula. Our margin of error is going to be a critical value, which I will talk about in a minute, times the standard deviation of the statistic. In the last chapter, we just spent a lot of time talking about the standard deviation of the statistics. So you know the formulas for these, and you're going to see them again. That then leads us into something called a confidence level. A confidence level is the success rate of the method used to construct the interval. How successful is the method we're using in constructing an interval? So the phrasing you would use, using this method blank percent of the time, commonly we use 95% of the time, the intervals constructed will contain the true population parameter. Right? That's what a level is, that blank percent. Now, there are some assumptions. Confidence intervals are not always appropriate, but there are some assumptions that have to be tested in order to determine whether or not a confidence interval is appropriate. So the first one is that the simple random sample from a population, the data that we're looking at, must be randomly gathered from a population or from a randomly assigned treatments from a randomized experiment. Number two, the sampling distribution must be approximately normal. So in that case, in order to determine whether something is approximately normal, as we did in the previous chapter, we have three options. First, if it's given, the problem states that the population is normal, that's great, we don't have to do anything. Or if there's a large sample size, remember the central limit theorem, that would tell us it's approximately normal. Or if we have the data, the sample data itself, we can graph it, and if the graph that we produce of our sample appears to be approximately normal, then we can assume the sampling distribution would also be approximately normal. And the third condition is that if we know the standard deviation. To construct a confidence interval, the goal is, what we're trying to do is we're trying to catch the central probability under a normal curve. So imagine a normal curve with the lines drawn in the middle, and the shading is in the middle of the curve. So we're trying to capture the probability under that curve. That leads us to our critical value. Our critical value is the number of standard deviations we have to go to the left and the right on the curve. That critical value is completely found from the confidence level. Okay, the upper z-score with a probability of p lying to its right under the standard normal curve. Alright, so for a confidence level of 90%, here's our picture. We would go out 1.645 standard deviations. So the 1.645 is our z-score, our critical value. Right, the tail area, if the confidence level is 90%, that means we're capturing 90% of the data, which means there's 5% in each tail. Okay, a 95% would look like this. We'd have 95% in the middle, we'd have 2.5% on the left and 2.5% on the right. That's 2 standard deviations, well actually it's 1.96 standard deviations, so the z-critical is 1.96. And then the 99%, imagine that, 99% in the middle, which leaves us with 0.5% on the left and 0.5% on the right. And there's our critical value we need. You should take a minute, if you need to, press pause, to write these 3 confidence levels and z-critical values down, because we use these 3 over and over and over again. By the time we're done, you will have these memorized. For right now, you should write them down. Any other z-critical value we need can be found on the bottom row of table C, which is in your textbook, and we will be looking at that tomorrow. Alright, so here's a confidence interval for a population mean. It starts off with x bar, that's our point estimate, the mean of the sample, plus or minus some critical value, one of the 3 we just memorized, or if we need a different one, we'll get it from table C in the book, times the standard deviation of the statistic, which you hopefully will remember from chapter 9 is the standard deviation of the population divided by the square root of n. So x bar is the estimate, the critical value, and then that is the standard deviation of the statistic. Those 2 things together are the margin of error. Again, you hopefully wrote all those down. Okay, so what does it mean to be 95% confident? What it means is that there's a 95% chance, well, asking you, does it mean there's a 95% chance? No, it It does not mean that. It does not mean that the probability that the interval contains mu is 95%. What it means is the method that we use to construct the interval will produce intervals that contain mu, the population mean, 95% of the time. So a confidence interval is all about the method. When we say we're 95% confident, it means we're 95% confident that the method will produce intervals that capture mu 95% of the time. Here are the steps for doing the confidence interval. First, identify the population of interest, the parameter. Number 2, address your assumptions. Is it a simple random sample? Is the sampling distribution normal or approximately normal? In order to determine that, it either has to be given that it's normal or has to have a large sample size, or the graph data needs to be normal, approximately normal. The standard deviation needs to be known. Name the interval, state the interval, and then conclusion in context. One of the great ways that you can remember these steps, because these are a lot of steps here, remember them is to remember the word panic. P for population, A for address the assumptions, N for name the interval, I for state the interval, and then C for conclude in context. Remember the word panic. It'll help you remember your steps. Alright, here's a statement. You should write this down and you're going to have to memorize it. We are blank % confident that the true mean, and then you're going to fill in the blank with the context of the problem, lies within the interval blank and blank. Alright, so that's you just have to memorize this statement. Don't get cute. Don't try and use your own words. Memorize the statement. And we're going to do lots of examples. Not tonight, but in class and over the next week. This is interpretation number 1 in your notes packet. Alright, so here's an example. A random sample of the SAT math scores of 500 California high school students yields a mean of 461. We know that the standard deviation for all seniors is 100. Construct a 95% confidence interval for the mean of all California students, and then comment on the meaning of the interval. This is a very typical, very standard type of confidence interval question. Here's what you would do. Remember the panic. Population of interest. It said the mean was 461. Address the assumptions. First, it's a simple random sample from the population. Told us that. Secondly, from prior experience, we know SAT scores are approximately normally distributed. And you can state that because we've covered it, we know it. And the third assumption is that the standard deviation is 100. And they told us that in the problem. Name the interval. This is called a one sample, 95% confidence interval for the population mean. And then we state, I give you the formula there. Using that formula, and we'll do more practice with the formulas and how we use them, but using that formula, we would get the interval 452 to 470. Finally, conclusion, we are 95% confident that the true mean SAT math score for California seniors is between 452 and 470. Notice the phrase at the bottom. I memorized the phrase, I provided the context, put in your numbers, and you're good to go. All right, we're going to do several of these in class tomorrow, but I wanted you to see this the first time tonight. Now, what can go wrong with confidence intervals? First, usually people just screw it up by saying the wrong thing. That's why I want you to memorize that phrase. What you can't say. You can't say the probability is 95% that the true mean falls between 452 and 469. That's just not right. The population mean is fixed. It doesn't vary. Right? Only the sample means vary. When you say that first sentence, that gives the reader the impression that you think the population proportion is the thing that's random, and it's not. Right? It's the interval is not fixed. The interval changes. The population proportion it's set. Don't suggest that the parameter varies. A statement like there's a 95% chance that the true mean is between 452 and 469. It sounds as though you think the population mean's wandering around, and sometimes it happens to fall between those two numbers. You can't say that. You have to make it very clear that you know the population parameter is fixed. It's the interval that varies. Don't claim other samples will agree with yours. keep in mind, confidence intervals, they make a statement about a true population proportion. Interpretations such as in 95% of samples of U.S. adults, the proportion who think marijuana should be decriminalized will be between 42.7 and 51.3. That's just wrong. The interval is not about sample proportions, but it's about the population proportion. Right? In 95% of the samples, the proportion who think, that's not true. It's the population. Your interval should be about the population proportion. Don't be certain about the parameter. Saying that the mean SAT math score is between 452 and 469. It asserts that the population mean cannot be outside that interval. We don't know that. We cannot be certain of that. We're pretty sure, but we can't be certain of it. Right? This is just an interval that was our best guess. And then don't forget, it's the parameter. Don't say I'm 95% confident that X bar is between 452 and 469. Of course we're sure that that's where X bar is. We know X bar. X bar is the sample, right? That's the mean of the sample. We already know that one. We're trying to predict the unknown population parameter mu. So be very careful with your symbols. Don't claim to know too much. Don't say I'm 95% confident that the mean SAT math score is between 452 and 469. We didn't sample all the students in the U.S. We only sampled California. This is where context is key. Don't overstate what you know. Be specific about what your sample was gathering data from. Confidence intervals are all about uncertainty. You are the one who's uncertain, not the parameter. Right? Not all confidence intervals you compute will capture the true value. In fact, about 5% of them will fail. So what you want to say is, I'm 95% confident that the true mean SAT math score for high school seniors is between 452 and 469. That gets the point across. Now, a confidence level. This is different about an interval. A confidence level is the level of confidence. It tells us the probability that the method produces an interval that includes the unknown parameter. If you're asked to interpret a 95% confidence level, which is a fantastic multiple choice question on the AP or on your test next week, if you were to take many samples of the same size from a population and construct confidence intervals for the sample statistic, then about 95% of the intervals will succeed in capturing the true population parameter. I could see that interpretation as a multiple choice question, where I would ask you which is a correct interpretation of a 95% confidence level, and I would give you 4 choices where I would just change the words around slightly. Instead of population parameter, put in sample statistic and switch the order and things like that. Great multiple choice question. You have to memorize it. You have to know it. Alright, that's all. That's all I have for you tonight. So hopefully you took good notes, and I will see you in class tomorrow.